pH. It's short for potential of hydrogen. At least, that's the leading consensus. And it is defined as the negative logarithm of the concentration of H+ ions in a solution. But why? Why does pH tell us about how acidic or basic a solution is? And why is it defined like that, of all ways? To answer these questions, we first need a basic understanding of what we're dealing with. An acid is basically a substance that donates its protons to other molecules. The hydrogen atom has one proton, no neutrons, and one electron. So if we just take that electron out, or in other words ionize it, we technically have a proton. So essentially the H+ ion is just a proton. Liquid water is held together by hydrogen bonds. The H2O molecules are tightly linked by these weak electrostatic forces between hydrogen and oxygen. Since oxygen is quite electronegative, which it means it's electron hungry, it pulls on the electrons of hydrogen, which holds it pretty meekly. This gives the hydrogen a partial positive charge and the oxygen a partial negative one. At room temperature, which is around 300 Kelvin, stuff starts vibrating a lot since temperature is directly correlated with energy. Due to this thermal fluctuation, what ends up happening is some water molecules snatch the proton from others when they get the chance, which we affectionately call donation, and this process is called autoionization. And so we have this dynamic equilibrium that is maintained in the water at all times. The AQ here just means that this is an aqueous solution. Stuff is dissolved in water. We usually write H+ as a shorthand for this hydronium ion. It's worth noting that this hydrated proton is very dynamic, so it can rapidly form fluid complexes rather than just this hydronium ion. What I mean to say is that the proton is almost never in one form the whole time. It may be doubly hydrated, triply hydrated, or even more at any instant. What doesn't change is that the thing is still a proton. It's just being very finicky. Anyway, so what the hell did we do all this for? Well, to measure how acidic a solution is, we need to look at how many protons we have per unit volume, and this, of course, is represented by its concentration. Well, more accurately, something called activity, but we'll get into that later. The problem with just looking at the concentration, though, is that only a tiny fraction of water molecules are actually ionized at a given time. For example, at 90 degrees, the concentration of H+ ions is of the order 10⁻⁻⁶. That's tiny. Since these numbers are so small, for the sake of convenience and measurement, we take the logarithm. Another thing is that this concentration can vary over many orders of magnitude due to how much the temperature affects the autoionization. A logarithmic scale makes these much more manageable. Coincidentally, the concentration of H+ ions at room temperature is really close to 10⁻⁷, close enough that we can say that its logarithm is approximately -7. But having a minus behind every single number is kind of annoying, so let's take the negative of the negative so we always have a positive number. And thus, the definition of pH is born. If a solution is acidic, it has higher H+ concentration than 10⁻⁷, so the negative of the logarithm is lower, meaning the pH is less than 7, and the opposite is true for basic solutions. But wait, rewind for a second. Didn't I say something about activity earlier? Well, the problem with just using the concentration at face value is that the actual functional amount of substance that is chemically available to react is usually not the entire physical amount of substance that we've got. In English, that means solutions are not ideal and dilute. Thus, instead of concentration, it's much more precise to say activity, which is in a way the effective concentration. Also, we divide it by the standard state so that it is dimensionless. In the ideal case, the standard state is just 1 mole per liter, or 1 molar. That's not the only reason we did this though. This is also to avoid having the logarithm of a number with a unit, which is not definable. And also so that we could ignore pure substances like liquids or solids which are already in their pure standard states, thus making their activity exactly 1, so they can be ignored. It's a little unfair to be treating water as a favorite child though. All we really talked about is the aqueous solution. So let's take a different solvent. Take the ammoniated solution, for example. A solution where the solvent is ammonia. It too auto-ionizes into ions like so. In this system, the ammonium ion acts like the solvated proton, making it the acid. So if we want, we could define a PNH4 to be equal to the negative logarithm of the activity of ammonium ions in the solution. It's not something we do very often, but we could very well do it. So really, pH is just one member of a much larger family of logarithmic acidity scales. If you enjoyed the video, please make sure to subscribe, or I guess more appropriately, like the video, and subscribing is like the next step, I think, right? Anyway, yeah, so bye.